Hi. All right. So today we're going to go over how you can calculate the surface area of different shapes. And we're going to look at the formulas that are available on your formula chart, but we're also going to sort of just talk about how surface area works if you were holding a three-dimensional object. So for example, the picture that we're looking at right here is a right triangular prism, and we say that it's a right triangular prism because the shape of the base is a right triangle. We see the 90-degree angle, and it's a prism because the shape of the faces are rectangles. This is an example of a triangular prism. You should have some of these at your campus so that you can look at the different three-dimensional shapes. Let's go ahead and think about what would this look like if we were to fold it out. So this is called the net. Whenever you take a shape and you flatten it to see all the sides. When we're talking about surface area, we're talking about the area of the surfaces. So when you're looking at this picture, you have a triangle in the front, triangle in the back, and then you have the three sides that represent what's called the lateral surface area. And you can flatten it out. This is called the net of a three-dimensional shape. So if we were to visualize what this would look like, you could imagine that we have these two right triangles, and then you have the rectangles that are coming off of the side. So I'm just going to attempt to sort of sketch this so you can see what that would look like. This is called a net if you were to flatten it out. And then you would have to imagine the different numbers and where they would go to represent the different side lengths. So for example, this would be 12, and we have 9, and then we have 16 would be this side over here. And then we would think about, well, what about this side that represents the hypotenuse? Because all of these sides are matching up. Like this 12 right here would match up with this side that would also be a length of 12, because whenever you're folding up the triangle, it's going to touch at that same side. So you have to visualize what are the sides doing that are meeting up like that. And if we don't have the hypotenuse, or if you have a certain part of the triangle or three-dimensional shape that's missing, you're going to have to think about what formulas do you know, or what different processes do we know about right triangles that would help us. So in this example, we have two sides on a right triangle. If we need to find the third side, you should be thinking, well, maybe I can use the Pythagorean theorem. So we're going to end up using the Pythagorean theorem here. So the Pythagorean theorem is a squared plus b squared is equal to c squared, where c represents the hypotenuse, okay? And the two legs would be a and b, so this would be our a and our b. Those are the two legs, and then we have our hypotenuse that's represented with c, okay? I'm going to outline that just so that it's a little bit easier for you to see. All right, so let's plug these numbers into our formula. So we have this side length of 12, and then the other leg is 9. So we would use our formula to add 81 plus 144, because 9 squared is 81, 12 squared is 144, and that's giving us 215. 225. That 225 represents the hypotenuse squared. That's c squared. So we still need to remember to take the square root of that final answer so that we can get the length of the side. So this is a side length of 15. And that's helpful to know because if we go back to our little drawing right here, this hypotenuse would match up with this side. So if you're trying to calculate the surface area looking at the net, or the flat two-dimensional version of that 3D object, you can think, I need to add a triangle, another triangle, and then you have 3 rectangles. That's one way to calculate the surface area. The other way that you could calculate the surface area is by looking at your formula chart. And this is what you're going to see as your formula on the formula chart. And hopefully this is okay. I just increased it so maybe you can see that a little bit better. Perhaps I should make it even bigger. Okay, there we go. Capital P represents the perimeter of the base. So capital P is going to be the perimeter of the base. The shape of the base is always dependent upon the side that is going to have a congruent side on the other side, and it's going to be parallel. So a lot of people are very commonly confused in saying that the shape of the base is whatever shape is on the bottom, and that's not necessarily true. When you're looking at this triangular prism, it's called a triangular prism because the shape of the base is a triangle. These two triangles are congruent in shape, they're the same sized triangle, and they're parallel. So they're not touching, they're on two parallel sides. So the perimeter is going to be whatever we get when we add the 12. We have a leg of 12, another leg of 9, and then the hypotenuse that we just calculated to be 15. So I'm going to write capital P is going to be equal to the perimeter, which is 36 here. Height. The variable h for height is talking about the height of the prism. That's very important to realize here. Height of the prism. Now, the height of the prism really represents the distance between the two bases. So how far are the two bases from each other? We're not talking about the height of the triangle. We're not talking about the height of the base. We're talking about the height of the prism itself. So if this is my prism and I have these two triangle bases, how far are they from each other? That's the height. And in this case, if the triangle is laying flat on one of the rectangular faces, the the height is the distance between the two triangles. So how far apart are they? And in this case, the height of the prism is 16 feet. Okay, so I'm going to plug that into my formula. So our H is equal to 16, and capital B stands for the area of the base. Area of the base. And that depends on the shape of the base. Now remember, the shape of the base is the triangle here. So when we're calculating the area of this triangle, we want to look at, well, what is the formula that we use for the area of a triangle? So a triangle is going to be 1/2 the base times the height. So if our base on the triangle is 9 and the height is 12, those are the numbers that we're using to find the area of the base. So we can say capital B is equal to 1/2. The base of the triangle is that side length of 9 times the height of the triangle, which is that leg of 12. So that's how we're getting 54 here. Okay, so we're getting 54 for the area of the base, height is 16, perimeter is 36, and you can substitute these values into the formula. Notice here on the formula it says 2b. So it's perimeter of the base times the height of the prism plus 2 times b. We're multiplying 2 times the area of the base because we have two triangles. Okay, and that comes out to be 684. And in this case, we're using feet, so that's square feet. Area is two-dimensional. So even though we're looking at a three-dimensional object here, when we're talking about the surface area, we're talking about the the flat surface, the two-dimensional flat surface. So our answer is going to be in square feet. Let's look at another example. So I'm going to clear this slide, and let's clear this one as well. Okay, so on this next example, we are now looking at a cylinder. So for a cylinder, on the last example, we kind of flattened it out to look at the net. You can also look at the net on a cylinder. So here's a cylinder. If you think about holding a cylinder or like a can of beans or something and you pop off the top, right? If you're opening up the can of beans, you have this circular base, that's the top, or it could have been on the side, right? Could have been on the left side or the right side. So we have two circles that represent the base on our cylinder, and then we can have our rectangle here that represents the lateral surface area. Kind of looks like a big division sign. Okay, so that's for a cylinder. So when we're looking at the net of a cylinder, you could calculate surface area as just being that you're adding two circles plus a rectangle, but you really want to understand where the numbers are coming from. Looks like the height of the cylinder is going to be 20. The height is the distance between the two bases. And we have a diameter of 8 because the diameter is the full distance across the circle. And if you wanted to, you could also kind of identify that your radius is half of that diameter. So our radius here would be 4 centimeters. Now, if you're looking at the formula chart, you're going to see something that looks like this. So we're going to have this part right here. That represents the part, if you think about the net, that part of the rectangle curves up to rotate around the circle. Do you remember what it's called when you're going the distance around a circle? The distance around a circle? That is called the circumference. So we're going to use the formula. So part of the formula is coming from the circumference because it's going to go around the edge of the circle. So the circumference is 2 times pi times the radius. That represents the circumference. So I'm going to kind of break apart the formula that we use here. So our formula for the surface area of a cylinder is equal to 2 times pi times the radius times the height, and then plus 2 pi r squared. And I want to explain where that's coming from. So the first part, 2 times pi times the radius times h, this is our h, that's giving us the area part for just that rectangle piece. And then when we add 2 pi r squared, it's because we have two circles. The area of one circle is pi r squared. So the area of a circle is pi times the radius squared. Okay, so now let's go ahead and plug in the values that we know. Cylinders are pretty easy to calculate. If we know that the radius here in this picture is half of the diameter, so that's 4 centimeters, and our height is 20, that's really all you needed to know there. The radius and the height, and that's giving you the circumference for the full cylinder. So once you plug everything into your equation, it's pretty easy to calculate the circumference or the surface area of a cylinder. Okay, here we go. So we plugged in a 4 for our radius, 20 for the height, and you're already seeing here on my calculator what we're getting. So our full answer would be approximately 603.1858 if we round. And since we're looking at centimeters, surface area is two-dimensional, so that would be square centimeters. That's an approximation. Now, if you wanted to leave your answer in terms of pi, what we could do here is, I'm going to copy and paste this so you can see. If I want to leave it in terms of pi, I'm going to get rid of the pi symbol here. So it's 192 pi. So what I could do, that would give us our answer without rounding, because we're leaving it in terms of pi. 192 pi square centimeters. See how that's giving us the same value? But that's leaving it in terms of pi. Okay? All right, now we're going to look at another example here. So this is a hexagonal prism. So now you're going to have to think, well, we're probably going to have to use trigonometry, right? If we want to calculate the area of a hexagon, we're going to end up using trigonometry, or you could use special right triangles, because the shape of our base here is a hexagon. So the formula for the surface area of a prism is going to be the perimeter of the base times the height plus 2 times the area of the base. Capital P, again, is going to represent perimeter of the base. And again, you could fold this out and look at the net. Perimeter of the base. You could look at the net. And here, because we are given the side length of 4, that's pretty easy to calculate, right? We have a hexagon, so there's a total of 6 sides, a side length of 4. That's going to be a perimeter of 24 meters. The other variable that we have in our formula is the height. Now remember that this is not talking about the height of the hexagon. We want to know what is the height of the prism. And the height of the prism is the distance between the bases. So our bases are the 2 hexagons that you see there. So our height is going to be how far is this hexagon. So this is one of our bases here. How far is this hexagon from this other hexagon? Because that H represents the height of the prism. And we have that given to us as 16 meters. Now for capital B represents area of the base. The shape of the base is a regular hexagon, because we see that all of the sides, this is an equilateral hexagon, all of the sides are congruent. So we want to follow the formula of 1/2 times the apothem times the perimeter, which we were doing last week. All of the math that we've been doing builds on top of each other. Okay, so 1/2, our apothem, we don't really see that in the picture just yet. Remember that the apothem is the distance from the center of the polygon to one of the side lengths perpendicular at a 90-degree angle. So I'm going to just leave that with the letter A. But the perimeter we know, right? We have a hexagon with a side length of 4. 4 times 6 is going to be 24. Okay, so now let's calculate what the apothem would be. So I have this hexagon, and let me just get a big hexagon here for us so we can sort of zoom in a little bit more. We have a hexagon. We have a side length of 4. This is our apothem. If we have a side length of 4, that means when we bisect the triangle to make it into a right triangle, so we could use trigonometry if we wanted to, that would give us this side length of 2. Okay, and we want to think about what angle are we going to use here in the right triangle to maybe use trigonometry. When we have a hexagon, if we were to do 360 degrees, because remember, we want to visualize all of the triangles that are coming here and meeting up at the center, right? So 360 degrees divided by 6 is 60 degrees. All of these angles represent 60 degrees, okay? But if we're trying to use a right triangle and we bisect that again, that means that this angle is actually going to be 30 degrees. If you're comfortable using the knowledge that we did with special right triangles, this is a 30, 60, 90 right triangle. This would be really helpful. You can tell just from looking at it that the 2, if I multiply that by the square root of 3, that's going to be the value of the apothem opposite from the 60-degree angle. But if you don't remember that, you can use trigonometry. So we have our opposite side and the adjacent side. So when you think of SOHCAHTOA, we would be using tangent. Tangent of the 30-degree angle is equal to the opposite side of 2 over the apothem. And then we're going to go through the process that we would use to find the value of A. A is in the denominator. We could do the reciprocal of both sides, which is 1 over tangent of 30, is equal to A over 2. So now we have A, our value that we're trying to solve for in the numerator, is being divided by 2. So this is algebra. This is just an equation where you're going to have to do the inverse operation so that you can isolate the variable, get A by itself. So if I multiply by 2 right here, that's going to be really helpful because these will cancel out and I'm left with A alone on the right hand side. If we multiply by 2 on one side, you gotta multiply by 2 on the other side. So we're going to multiply 2 times 1 over tangent of 30, which ends up just becoming 2 divided by tangent of 30. So you can use your calculator here to help you solve. So I'm going to say A, our apothem, is equal to 2 over tangent of 30 degrees, and our calculator is already in degree mode. So notice here that's the same as 2 times the square root of 3, right? You see how those values are the same? So if you know those facts with the 30, 60, 90 right triangle, that helps you out a lot. It'll save you some time. Okay, so capital P was our perimeter of the base. We already know that that's 24. Let's kind of simplify this. We have 2 area of the base. I'm just filling in the variables that we know. And then we're multiplying that by 24. So these 2's cancel out. We're left with 24 over tangent of 34 to represent the area of the base. But I'm going to go ahead and use the variables that I'm assigning here in the calculator. So capital B is 1/2 of the apothem times the perimeter. And we just need H. So our H is the distance between the 2 hexagons, which is 16 meters. So now it's filling in all of the variables that I'm assigning. We have capital P, perimeter of the base, capital B, area of the base, H, the distance between the 2 hexagons. A was my apothem. So we're getting approximately, let's do this in a different color. We got a lot of colors going on. So we're going to get approximately 467.138 square meters. Area is 2-dimensional. Here we go. All right, so we just did 3 examples. On this last one, I want you to go ahead and attempt to solve it yourself. So let me clear the screen. Actually, yeah, let's you can do this. You guys can do the pentagonal prism. Okay, so let me write the formula for you here so that you can get started. So surface area is going to be the perimeter of the base times the height plus 2 times the area of the base. And let's identify those variables here. So P is the perimeter of the base. H is the height of the prism, which is the distance between the two bases. How far are they from each other? Capital B represents the area of the base. Okay? And let's even go a step further here. The shape of the base are the two sides that are going to be parallel to each other and congruent. So here, when we're talking about the pentagonal prism, these pentagons are parallel to each other and they're congruent in shape. So they have the same shape, same size pentagon. Okay. So we're going to be, I'm already noticing to calculate the capital letter B, we're going to need to use trigonometry to find the area of the pentagon because we need to know what the apothem was going to be. So I'm going to pause right now so that you can do that. Okay, now let's check your work here. So capital P, perimeter of the base. The perimeter is going to be 14 times 5 because we have the pentagon has 5 sides, one side length of 14. That's going to end up being 70, right? Let's double check here. So perimeter of the base, let me type the full formula. Perimeter of the base times the height plus 2 times the area of the base. Perimeter of the base is going to be 14 times 5, 70. Height is the distance between the two pentagons. So how far apart are they? Well, according to this, they are 11 centimeters apart. 11. So I'm going to go ahead and put H is equal to 11. Capital B is the area of the base. The shape of the base is a pentagon. So we're going to use 1/2 times the apothem times the perimeter. We are going to use some trigonometry to calculate for the apothem, but the perimeter is 70. We already got that value. So I'm going to write here that the area of the base is 1/2 of the apothem times the perimeter. So we still need to identify what is A. What is the apothem? So the apothem is the distance from the center of our polygon perpendicular to one of the sides, and we're using a right triangle to help us here. This is our apothem. So you first need to figure out what is the angle that we're using at that center. Well, if you have 5 sides on our polygon, so we're going to divide this by 5, and then that gives us 72 degrees. Well, 72 degrees would be if we were looking at one of those isosceles triangles. If we want to bisect that and make it a right triangle, we're going to cut that in half again. So that's where the 36 degrees is going to come from. And when you bisect to create that right triangle, instead of using 14 centimeters, we're now using 7 centimeters because we're bisecting that side. So this is 36 degrees. We want to solve for the apothem, very similar to what we were doing on that last slide. So we're also using tangent because 7 represents the opposite side, A represents the adjacent side. Tangent of our 36-degree angle is equal to the opposite side over the apothem, or the adjacent side, which is A. To manipulate that with algebra, we're going to end up having 1/2 times, let's see, am I going to have enough space to write this? This will end up being 7 divided by tangent of 36 because you have to rearrange that equation to solve for A, and then we're going to multiply that by the perimeter, which is 70. Okay, so I'm going to plug into my calculator that my apothem is equal to 7 divided by tangent of 36 degrees. And now that we solved for the last variable that we needed in our original equation, you can see that our final answer is popping up. So let me record that. This is going to be approximately 1,444. That's a lot of fours. 0.427. Area is two-dimensional, so that is square centimeters for our final answer. All right. Good job, guys. You did great today. Thank you.